I extend a very warm welcome to today's resource person, entire human you from the crowd circle. I also extend a welcome to our body trustee, Dr. Dev, principal of our institutions, Dr. Sagar, Dr. Amardeep and Dr. Sundar. Please clap loudly for all Now we will all, I request everyone to cover their heads and will be having prayer. I request students of public school will seek blessings of the Almighty before starting our program.
ਵਾਹਿਗੁਰੂ ਜੀ ਕਾ ਖਾਲਸਾ ਵਾਹਿਗੁਰੂ ਜੀ ਕੀ ਫਤਿਹ।
I request Madam Principal, Khalsa College for Women, Cinema, Dr. Sundar Kaur, to accord formal welcome to today's resource person, Dr. Payal Lamakal.
वाहिगुरु जी का खालसा वाहिगुरु जी की फतेह. It is matter of immense pleasure and honor for me to welcome eminent scholar Professor Raphael, whose intellectual contribution in the field of physics is excellent and widely acknowledged. On the behalf of Honorable Shri Guru Hargobind Ujagar Hari Trust, faculty and students of Sidma Group of Institutions, I extend heartiest welcome to our distinguished guest, Professor Raphael Ji. Dear guest, I would like to say something about our trust, and I would also like to enlighten you about Shri Guru Hargobind Ujagar Hari Trust history. The sapling of Sidma Group of Institution was laid by side by Narayan Singh Ji, legendary personality. He laid a sapling in 1909 when Sikh Girls Senior Secondary School was started with the visionary thought of women empowerment and education. When educating women or educating female was rarely accepted in Indian society. His wife Bebe Ram Kaur Ji, daughter-in-law Bibi Atar Kaur Ji, his daughter Bibi Har Prakash Kaur Ji, who got Padam Shri award from the Government of India, carried forward his noble mission. It has now flourished into a big tree of 6 institutions running under the aegis of Shri Guru Hargobind Ujagar Hari Trust Management. Again, on the behalf of Shri Guru Hargobind Ujagar Hari Trust and Sidma Group of Institutions, I heartily, warmly welcome you, sir, in this event. Over to Dr. Gagandeep Dhane ji.
Before we request Sir to deliver his lecture, I would like to give a brief introduction about Dr. Raphael Blumenfeld, who is an eminent scholar, and when I was going through his biodata, it ran into 23 pages. Sir holds nationality of UK and Israel, and he's done his PhD from Tel Aviv University. Sir is well versed in English, Hebrew, Romanian, Chinese, and is a beginner in learning Esperanto language. And currently, he holds many prestigious positions, and these positions include: presently, he is Director of Studies for National Science, Gorbel and Kai's College, Cambridge University, Senior Research Fellow, Imperial College, London. Presently, he is also Editor, Granular Matter Journal, Springer, and College Lecturer, Gorbel and Kai's College, Cambridge, UK. Research Fellow, Earth Science and Engineering, Imperial College, London. Long-term visitor, Cavendish Laboratory, Cambridge University. Apart from these, he has also held many important positions in different universities from time to time. Sir has been awarded various honors. Various honors have been bestowed on him, and these include: he was awarded High-Level Foreign Talent by China government. He was awardee of 1000 Talent Plan by China government again. And he was awarded Alan Howard PhD Student Scholarship, Bi-Fellow, Gonville and Kai's College, Cambridge, Nuffield Undergraduate Research Bursary, and Alan Howard PhD Student Scholarship. He's also got Director's Fellowship, Los Alamos National Laboratory, also got Leo Baik Lodge Award, and Baylor Foundation Scholarship Award. Apart from these, he has also received various grants for his projects. And he's also been associated with various research activities, like he has organized around 40 international seminars and conferences. Such as chaired sessions in various conferences and seminars. Regarding his PhD research supervision, he has supervised till date more than 50 students for their research. And to summarize his publications, Sir has over 110 papers in primary peer-reviewed journals and 28 contributions to symposia and compiled volumes. A huge round of applause, please, for Sir. Sir has also been invited as resource person in more than 82 international conferences and workshops. Sir has also been part of invited colloquia and departmental seminars. And when I was going through his resume, one very interesting thing that Sir has written is that I have told you about his research work, about him as a scholar, but very astonishing thing is that apart from science, he has passion for volleyball and chess. He has played chess in various international events, and he has also coached teams of volleyball. This was something very unique about him. Now, without much ado, I would like Sir Raphael Blumenfeld to come to dais and deliver his lecture. Sir, please.
Thank you very much for inviting me, and thank you for the very kind introduction, especially about volleyball. I was a semi-professional volleyball player before I saw the light. First, I was invited here to talk about physics, probably enthuse you about physics. So let me first say a few words about myself. I'm a theoretical physicist. I do most of my work in statistical physics, which means looking at systems that are disordered. These are the ones that are of interest to me. Complex phenomena. and essentially looking at everything around you and trying to model it. This is what physicists do. We look at what we think is reality and trying to model it. We're not looking for the truth. We're looking for always for a better model to describe reality as we see it. Some of the problems that I've been working on involve spin systems, spin being a property of some atomic particles, magnetic systems, as I said, complex phenomena, pattern formation, self-organization. Self-organization is a very basic concept in nature. Each one of you is a self-organized system. It's not a chaotic system, it's a system that's self-organized. So this is something I'm very interested in and working on. And some things that may look very simple, sand, granular materials. Granular materials are ubiquitous in nature. In fact, they are the most ubiquitous substance on Earth after water. Yet we don't understand how it behaves. If you go on the beach, you hope that the sand will hold you. In other words, it will behave as a solid. But when you put it in an hourglass, it flows. We don't have a clear understanding, or at least a clear modeling, of how sand behaves, and in general, how granular materials behave. So this is something that you can talk to a 10-year-old, but if you try to do the physics of it, there's quite a few very brilliant minds still working on it. It's still on the frontier. I'll show you some of these probably later on, some pictures of them. I've done many things. This is the advantage of being a theoretical physicist. You can do a lot of things, not necessarily in physics. Studying physics opens a lot of doors. Many of my colleagues went on to finances, to banking, even in biological sciences. Well, physicists, we as physicists are a bit arrogant. We think we can do anything. So some of my colleagues do biology as well. But it is an advantage. Physics is, at least to me, is one of the best adventures there are. Some of the problems that I've been working on, or people work on, are either very challenging theoretically, or very helpful technologically, or simply very interesting. We're doing things and sometimes we don't know what it's good for, but just for the pleasure of it. So I'm based in Cambridge. Incidentally, all this long introduction just tells you that I'm simply old. I managed to do a lot of things. It just means that I'm old. You know that. So I come from Cambridge. Cambridge has colleges. My college is Gonville, and it's pronounced Keys for some historical reason. Gonville and Keys is also the college where Stephen Hawking was. In fact, his door was next to mine. Not that we talked a lot, we talked a bit, but it's very difficult. It was very difficult to talk to Stephen Hawking. Every conversation takes a very long time. So it's one of the colleges in Cambridge. Colleges in Cambridge admit students. It's not university that admits a student in Cambridge, but rather the colleges. So many young people of your age pass through me in interviews to the university. That's the system. The advantages of going to university, there are plenty of advantages. Other than the fact that the university sort of gives you knowledge, you study things, it's also something beyond that. It opens your horizons. if you go to university, you are on your way to become independent. You're away from your parents, you need to now get involved in a company of other people your age. You don't have your parents to help you and support you. You need to tend to your own lives, you find your own food, you buy your own things. You manage. University is a fantastic place to mature, and it's completely different. You meet new people, you meet new friends, you network. Network is sort of not a great word these days, but it means that you find sometimes people that you can go through life with, either friends or colleagues, or some people that you enjoy to be with. What else can I say about that? The other thing that's good about university that there are around you people who are knowledgeable about many things. And if you talk to these people, eventually you might find the thing that fascinates you, the thing that you would want to follow. It happens, not necessarily at the beginning. Most people go to university, don't really know what they want to do. They start with something, but then they move to something else. I didn't know that I wanted to be a physicist until I was in my early 20s, really. So, yeah, let me show you some of the things that I've done on the simplest thing, granular systems. I mentioned hourglass. Okay, an hourglass, you know what an hourglass is. It's something that measures time. You put sand or salt, it goes down, and it measures when is your egg ready. Why can't we do it with water? Why do we do it with sand or salt? Can anybody know? Do you know why? Anybody? I mean, we could easily put water and let the water drip there. No. The reason is that this is a time measuring device. If you put water, as it goes down, the pressure goes down and the rate of flow changes. That's not something good in a time measuring device. Yeah? If you put salt or sand, the rate is constant, always to the last 10 grains. In other words, granular materials, sand, salt, powders, the asteroids, they behave sometimes like fluid, sometimes like solid, like on the beach. But we don't really know how to write the equations of how these things flow. There's a lot of debate now on that. There are models. So let me show you now some of the things that happen in granular materials. Although having said that, granular materials is not only things that are of the size of microns. I can look at the cosmic web and it behaves quite similar to granular matter. And I'll talk about this in a minute, maybe more. Can I just put down? younger than me. Sorry. I hope you didn't go to sleep after all this rearrangement. Yeah, as you can see, physicists can connect things. We're not completely clueless about engineering. Right, so after all I've said, I wanted just to give you some examples on things that look very simple, but scientifically they're very complex to model. And one of these is something, as I said, that you played as children: sand, grains, powders. And these are things that are all around us. So this is a talk I gave a while back. It's a huge talk. It will take me 2 hours, and I'm just going to... This needs to be a bit... Okay, I hope you don't mind all the noises that it makes. That's not me. So here you see some examples of the things that can be done and are being done and are being explored currently in physics. It doesn't look like black holes or dark matter or dark energy. On the one hand, it doesn't look like elementary particles, quarks, but one can learn a lot from these simple things that are around us. Sand, coffee, all these are granular materials. What you see here on that side is actually biological cells. If you look at a couple of biological cells, this is what you see there. This is a... Do you have anything that I can point to? I'll use this as a pointer. So, can you hear me if I move away? Can you hear me there at the back? Someone shouts, what? Right, so what you see here, can you see the cursor? Doesn't see the cursor. Right, so what you see here, where I do with the cursor, is biological cells. Thank you. So these are biological cells. What you see here, can I use this one? This is even better. Okay, this is much better. Right, so what you see here is a drum. When it rotates, you have two different types of particles. One part of particles is just slightly larger than the other. As you rotate, they create this pattern. They segregate into two materials. This is what in thermodynamics, what you would call phase separation. Things separate like oil from water. They do this here not because of interactions, only because the sizes are different. And you can describe this what's called open cells, something like that. So I'll just show you things. I'm not going to throw on you equations. So what you see here, again, is foam. This is a foam. You treat a foam with the same models, or very similar models, that you treat particulate materials. And they're very fascinating. This one is another foam. This is the hourglass I was telling you about, where the sand pours down at a constant rate, which water cannot do. This is just sort of, when you talk, when I gave this talk, of course, there were some people in the audience who, from funding agency, and then as physicists, we like to do physics, or on the other hand, we are compelled by administrators to also get funding. So we need to sort of convince program managers that these are important, not just to our enjoyment, but also to get funding, to make money, how it is important to human life. So in transport, handling, and storage of granular materials, this costs trillions of dollars only in the US. Now this talk was this was about 10 years ago, so by now it's much more than that. Landslides, granular materials. Landslide cause a lot of damage, including to human lives. Billions of dollars around the world. 10% of the world's energy goes towards handling particulates, and 50%, now this now is slightly less than that because there was a push against fossil fuels. So 50% of the world's energy resources are extracted from soils and rocks, which are granular materials. Yeah. Transport of particulates in all technologies, almost everything one does, everything you buy, at some point in its life went through a particulate form. So here you have this thing. They operate at relatively low efficiency. So knowing this, you can help. As I say, these are the things that you sell to program managers. So every technological process, every technological material actually passes through such a phase, of particulate stage. So this means that any little progress one makes here can make a huge difference. Funding program managers, give us money. That's essentially what this means. Okay? But the main problem for me, which is more important than all of that, is the theoretical understanding of these materials is very poor. We don't know how it flows, we don't know how it supports stresses. If I run on the beach, I hope that the sand will hold me. In other words, it will be a solid. I hope it doesn't turn suddenly into a liquid, will flow, and suddenly I'll be in a quicksand. In other words, when does it turn from a solid to fluid? We don't know very well about that. We call it a jamming transition, but it's just a name. Let me pass through this. This is not. So these are the things that I do in this. Don't be put off by words, but essentially I'm trying to develop a continuous stress theory. In other words, if I put a stress on a box of sand, say, how is the stress transmitted? Now, you must have heard of elasticity theory, Hooke's law, and if you go to university, they'll keep hammering into you elasticity theory. It doesn't work for these materials. Simply doesn't. So I'm trying to develop a continuous stress theory for such materials. Now, statistical mechanics. I'm sure most of you haven't heard of it. Statistical mechanics is one of the most powerful tools in physics. It tells you that if I do the statistics of all the molecules in this room, and I do the correct statistics, then I can extract large-scale properties like pressure, temperature, volume, in other words, equation of state. Okay? So this is all based on what's called statistical mechanics, which works for equilibrium systems. Some of the things that I'm trying to do is extend it to non-equilibrium system. Non-equilibrium meaning not the state, for example, of the air in this room. Statistical mechanics tells you that you can go into this room and you don't sniff to see maybe all the oxygens are in the corner there. Because if they're in the corner, of course, you'll breathe only nitrogen, which is not very healthy to your health. Okay? You expect when you go into this room, all the oxygen to be sort of uniformly distributed in the air here. In fact, you put your lives in your hands, but as you just go into the room. Okay, so this is all based on statistical mechanics, or the description of it is based on statistical mechanics, and you hope that this is in equilibrium. Sand, granular materials, the asteroids around any planet, they're all granular materials, albeit on a much larger scale. Okay? The Earth is one particle, if you think about it like that. So, how these things also fail and yield if I put my foot on the sand, it rearranges itself and then it supports me. It's not like this floor, I put my foot, the floor doesn't change. Okay, so how does this happen? When does it fail? All these are questions that I'm looking at, and recently I've been involved in discovering that actually these materials self-organize in the sense you do something to them and they sort of self-organize. The self-organization is a concept from what is now called mostly complexity theory. So, to self-organize means to form some pattern in response to some driving force or to some external constraints. As I said about 10 minutes ago, each one of you is a self-organized system. You self-organize, you have cells, you have a hierarchical structure, and you self-organize into what you are today. Okay? So, how do these things happen? What drives it? Can we have a general theory? Right now we don't. I know how to do it roughly, so to speak, in this context, and I'm working on how to do it in general. And for example, another example of self-organized system is if you walk in a very crowded space and you want to get from A to B, and most of you want to, you'll realize that if you look from above, most people start to walk in a lane because this is the easiest way, you don't bump. And suddenly the whole, it's not chaotic. If you have lanes forming, there's no external engineering of this phenomenon. It's on a local level. This is what we call self-organization. The whole crowd self-organize into walking into these lanes. Pattern formation is also part of this self-organization. Maybe I won't go. In order to do something in granular materials, you need to know how to quantify structure. We say structure, it's a word. We need to quantify things. So this is on a general, more general thing. Mathematics is the language of physics. There's a difference between mathematicians and physicists. We, as physicists, use mathematics. They, well, depending if they are pure mathematicians or applied mathematicians, they do mathematics because they like it mostly. Because it's helpful to anything. For us, this is just a language. So, in order to do something with this language, you need to have quantities that are quantifiable with numbers. In other words, we need to put mathematics. And this is what I tell to students. You get a question in a native language. You need to translate it eventually to equations. In other words, you need to translate to this other language called mathematics. Then you crack the handle, mathematics gives you a result, and then you raise your head and say, what does it mean physically? Does it make sense? Sometimes it doesn't, often it doesn't, at least in physics. So this is just a way for me to quantify structures. I'll skip that. This is a nice pattern actually. This is one of my methods to quantify a system of fracture, and it gives you, I'm showing it just because it gives such a picture which is very pleasing to the eye. But it's essentially each one of these colors has, okay, I'll throw a frightful word, has a tensor attached to it. In other words, a set of numbers that tells me something about the shape of this particular element. Again, quantifiable. You need to quantify things. So you can do the same thing in three dimensions. I'll pass through this. Let's see. Where do I go with this? And then you use this to sort of look at differences between things. These are two different systems, so you use this description to show how these two systems are different. They don't look so much different, but this one is packed much more densely than this one. And indeed, if you look at this particular system that I showed you, it shows it. And more interestingly, these are two phones. They're both generated virtually on a computer. This one is completely random, and if you look at this description, that the distribution of some volume element looks like that, but then you let it minimize the energy. The phone, what happens is that the surface, the walls of the cells, they have surface tension, so they contract to minimize the energy. And there's a system online, or a software online called, I forget, something evolver, surface evolver. You do that and it comes out to be this kind of form, and then you do the same, try to quantify with the same description, you get something completely different. In other words, this method can distinguish very easily between two different structures. Forget the equations, this is statistical mechanics, but I just want to say this was my mentor, Sir Sam Edwards, who essentially single-handedly opened three major fields in physics. One was, he introduced ground material to physicists. This was in the late 80s. He essentially created the field of what is called now soft matter with Pierre-Gilles de Gennes, who got the Nobel Prize, and in a Nobel laureate talk, he actually mentioned that all he did was actually solve the equations that Sir Sam Edwards developed. So he was essentially my mentor, a very great man who died in 2015. What else can I say about that? Forget that. Right, and here are very particular examples of what happens. What you see here is two-dimensional photoelastic particles. These are particles that if they allow the light to go through them, okay? But if I now put cross-polarizer, light is polarized, okay? Now, if I put two cross-polarizers like that, one polarized this way, one like that, no light is coming through. But then if I take the light itself and start to move it a bit to shift the polarization, some light will come through. Okay? What you see here is some polymeric material, photoelastic, that if you strain it, it changes its refraction index. As soon as it does that, the polarization changes a bit, and then something comes through. So what comes through here is essentially the places where you have a higher strain. In other words, the places where you also have a higher stress or higher forces. So when I do that and I start to shift, I start to see where the forces go inside this material. So this is what you see here. It's essentially a signature of where all the forces go. We call these force chains. Now the interesting thing about these force chains, they follow nothing like elasticity theory. Elasticity theory gives you sort of very nice smooth waves. Nothing like that. I will show you, hopefully this will work. I don't know if this movie will work here. So, okay, let me just go out of this and show you a movie. So, this is a movie of, okay, what happens here, let's take this, where will I put this? I'll put this here. Right, what happens here, I have this photoelastic material, and I'm moving, it's not me actually, this was another great experimentalist by the name of Robert Berenger, who also died recently, unfortunately. So you move something like that, you shear the material, and I want you to watch what happens to these force chains. What you see up here, I don't know if you can see, but this is the force against time. And what you see is that, hopefully, okay, so now the movie works. So, if you notice here, the force starts to increase. I'm moving this, the force increases, not much is happening. What's happening is just these force chains become stronger and stronger. And then suddenly one of these force chains breaks. It shifts and suddenly everything moves. Then it moves, you see the force increases, now something breaks again. You see a much larger movement now. Bang. And it goes on. Let's go all the way to this and then I'll stop, otherwise it's a long time. Okay. So the force increases. Just watch what happens when it fails suddenly. Something fails. You'll see a major rearrangement. And bang, the whole thing moved. Okay, so this is not an elastic behavior. Definitely not. Stop that. Where was I? Right. So, I don't want to bore you too much with this. This is another example why understanding how granular material flows is so important. You have these silos. This silo is just collapsing, it was called. So what silos are big containers that contain grains. In this case, grains of wheat, of corn, of whatever. And what happens is that the pressure, unlike in water, if you go in water, the pressure just goes down. It increases with depth linearly. It doesn't happen like that. Because of these chains that you saw, the chains actually lean on the boundaries, or suddenly all the force is on the envelope rather than in the middle. In the middle, actually, the stress is pretty low. And because of that, because the area, the section area is low, these fails. So you see these silos collapse, huge damage, huge loss. And that's another case of very important, I should say application, but it's a very important hazard. Landslides, you have this landslide that covered quite a lot of houses here. Very important to know when it happens, why it happens, how to avoid it. Forget about that. This is all theories of what's going on. This is the one and only experiment that I did in my life. It was published. It's a very low-tech experiment, which I'm proud of. But as a result, because I had to look at all sorts of stuff, I had to buy some new glasses afterwards because my eyes were not as good afterwards. What else I want to show you here? That's something in the Science Museum, probably another movie that won't work. There are plenty of other stuff probably here. Yeah. Okay, I won't bore you with more of that. Yeah. So, granular material. In space, you can ask yourself how planets, or rather smaller stuff, planetesimal or asteroid, how do they form? They form by small particles coming together at very low gravity. Eventually, they come together, they form a small aggregate. The small aggregate has a larger mass, so it attracts small particles, and it grows like that. Because it grows at very, very low gravity, it's very porous. In fact, about 95% of the asteroids that we know about are called rubble pile asteroids. They're very porous. And because they're porous, they behave like these materials and not like solid blobs. And NASA and other space agencies are only now coming to terms with that. You know, like this is another thing that I've done recently. It's a paper about if you try to nudge such an asteroid, which is the current strategy to avoid collisions with Earth, is not to blast an asteroid. Because what happens, if you blast an asteroid, it may break into bigger particles, bigger parts of it, and then it's more dangerous than the asteroid itself. So what the most common strategy is to try to deflect it, to try to shoot some projectile at it and sort of deflect its trajectory to miss Earth. The problem is that if it behaves like these materials with force chains, if you hit it at the wrong place, even at very small impact momentum, you can still break it because of the shear stress along the force chains, and then it can break into 2-3 parts, which is even more dangerous, as I said. So understanding this is now an issue that I've written about. So the point is, granular materials go all the way from the sand or from micron particles to asteroids. And in fact, if you look at how particles, or when I say particles, I mean planets or objects, aggregate, you'll find that this potentially could explain what we see as the cosmic web. Maybe not all of you heard of the cosmic web. If you look at matter in the universe, you'll find that it's not uniformly distributed. It's distributed like a web, with places which are slightly more dense in other places. And the question is, how did this form? Why is it not uniform? Well, the answer is we don't understand it. But part of it is potentially because of how these things aggregate. So, yeah, so that's to impress on you that that's one of the things that I do. There are other more crazy things that I do that I would not hit you with. I don't want to come as a complete lunatic here, but just because I like doing that. So to conclude that, I'm just trying to give you a flavor what a physicist's life is all about. It's about, well, I hate it, but it's about having fun. So I'm having fun. I'm semi-retired now, but I was lucky enough for people to give me money to keep doing what I'm finding is fun. To me, it's that I never take it for granted. It was a privilege. It has been a privilege. I'm still doing a lot of research. So to become a physicist or a scientist in general, you need to really want it. Because, okay, you're students in school, so obviously you're bright people. Most of you could probably make money outside the academia more than having this fun in the academia. So to want to do this, you really have to be a bit crazy, really. But you really need to want it. But that's not to say that it's useless if you decide you don't want to be a scientist. If you go to university and say, I'll start with science, I don't know what I want to do, but I'll start with science, you'll find that the tools and the skills that learning science gives you are useful in many other areas. As I started to say before, many of my colleagues went to banking, I mentioned that, to finances, simply because they knew how to use this language, mathematics. They knew how to solve differential equations, but more importantly, they knew how to approach a problem. The skills of approaching a problem are very important in many other fields. So, physics in particular and science in general opens a lot of doors. Even mathematics, not science. Mathematics is not a science really, it's something else. But knowing mathematics opens a lot of doors. Well, you should notice in India, you had Ramanujan, yeah, world famous. So, that's about it, but having said all that, you don't really, to be successful, you not necessarily need to go to university. There are plenty of successful people who didn't go to university. Well, my eldest son is one of them. Yeah, he started in university. After the second year, he came to me and said that, look, actually, he went to computing, said, sorry, my lecturers have nothing to teach me. I can teach them something, so I want to drop out. And now in the UK, the students pay money. So essentially he was accumulating debt. So I don't want to accumulate debt. And he says, look, this is not physics. In computing, you don't really need a certificate. You need experience. He dropped out. He's a very successful chocolatier now. After building also many web pages and all stuff. Makes a lot more money than I do, than I ever did, but he's very successful. And I know quite a lot of people who didn't go to university and were successful. So I'm not saying that all of you should go to university to be successful. Go to university for the things that I mentioned before. Broadening your horizons, meeting new people, maturing, being independent. So breaking slightly away from the dependency on parents. Yeah. But success comes in many ways. So I think I'll stop here. I took too much of your time probably. Thank you for being very patient and listening to me. And the last thing I want to do is, if you have any questions now, I'd like to get questions from you, which I will try my best to answer, about anything, about the physics, about university, about life in general, I don't know. So, yeah, the floor is yours. Thank you. Can we have someone going there with
So when did you figure out that you wanted to be a physicist or a scientist in general?
Sorry, you'll have to be, even with the microphone, you have to speak a bit louder. That's a simple question with a very long answer. I started by, when I was a teenager, I really liked sci-fi. And I read sci-fi. And then I read a book. It's pretty random, really. I read a book, and the hero of the book was a philosopher and physicist, and I said, oh, this is a very nice life. And then I didn't go to physics, I went to engineering. I had a technical high school, I went to engineering, I did this, and then realized that it's not that interesting. It was interesting, but not for me. And then I realized that actually if you're a physicist, you can travel the world at the expense of other people. So that was my... So, hang on, but this is how I started it. And then I started to do it, and I fell in love with it. More questions on anything, really. Question from this student here.
Does physics have any role in pharmaceuticals?
Does?
Physics has any role in pharmaceuticals?
Yes, there's several aspects of it. One is even the ground materials. When you have pills, you compress them. Now, you cannot compress them too much, because if they're too compressed and you, let's say, swallow a pill, it just passes through your body, it doesn't do anything. If it's too dilute, too fluffy, it sort of dissolves in your mouth, it doesn't get where it needs to go in your gut. So, how much you compress, so that's mechanics, it is quite important. Now, the pharmaceutical companies work on this quite a bit. That's one thing. The other thing is that in physics we had for a long time something called a field. We tried to see how protein fold. Protein is a chain with amino acids, and they have a particular structure, and each protein has a function. We don't understand the function of most proteins, but we know that if you now stretch it, it loses its function. It's called denature. So now we have artificial intelligence trying to predict for us what kind of proteins we can form. So AI sort of spits out a lot of structures and then try to correlate this to functions. And some of the functions are useful. So yeah, some of the current, not the current, maybe the future, the near future medicines are actually built from this kind of material. I have, for my sins, I have 2 papers in biology about stresses in the cell, the cytoskeleton of the cell, which admittedly didn't go to the pharmaceutical company, otherwise I would be much richer. But it does allow us to understand how stresses propagate from the membrane of the cell to the nucleus, which was, at the time at least, was not very well known. So, and this is also very useful for pharmaceutical companies. There's a colleague of mine who built a whole company, a physicist, built a company using machine learning to correlate between effects and drugs, and effects and substances that can form the drugs. So yes, there are plenty of physicists actually working in the pharmaceutical industry. Thank you for the question.
Sir, there is a subject econophysics.
Sorry, say it again?
Econophysics.
Now, econophysics is something you probably saw this online. But I was involved in econophysics. Economics is a very chaotic and self-organized system, in the sense that there are plenty of stuff that you cannot predict. For example, the share market. It's very difficult to predict the share market, and the reason is very simple. The distributions are not very narrow, they're very long tail, which means that the average is not a good statistics. If fluctuations are very large, one fluctuation can dominate the whole ensemble. Econophysics also deals with how technology develops, how creativity develops. What happens is that you have sort of incremental knowledge increasing, and then suddenly there's a breakthrough. The transistor, for example, and immediately it's an avalanche, it leads to an avalanche of technological applications. So this is part of econophysics. There are plenty of aspects. Econophysics is simply such a huge area. It involves almost not only finances, but how we arrange societies around economics. And then if you think about the evolution of the development of cities, they are very intimately connected to how the economics grew. And economics is, part of it is self-organized, part of it is constrained from by politics, and all sorts of decisions that have nothing to do with it on the personal level. So yeah, econophysics is a huge subject. Quite a lot of physicists working on this, as well as economics. A personal favorite pet of mine, which I was trying for a while to convince an economist to look into, is to try to develop a system or a computer simulation of two populations, one of administrators and one of workforce. Because this is what we have in most institutes. We have a workforce, doesn't matter what the workforce does, and we have administrators. And the evolution is always, it follows similar patterns all the time. If you look at Amazon or Google, it starts from very nice, very small nucleus of the workforce. Some people have ideas and they develop, but then they start to be successful, then they need HR, they need accounting, and they need also the administration grows, and the administration develops according to different dynamic rules than the workforce. So far, I haven't managed to interest any economists in trying to simulate this, but that's another possibility for economic physics. Yeah, I know plenty about this. Thank you.
So it's just a basic question. So when your son came up to you and told that he wanted to drop out of university, how did you react? And how, like, you will teach parents that how they should react when their, like, children will come up to them and tell their feelings?
I will not regard myself as wise as to tell other parents how to react. I can tell you what I did. It depends very strongly on the personality of the parent, or the personality of the child. How did I react? What I said to him essentially is, look, a certificate in physics is a plan B. You want to do other things, that's fine. But if you don't succeed, then you have a plan B, you become something. He didn't want that. He said, doesn't matter, I will succeed. And he managed. So, he was pretty clever, still is actually. So definitely makes a lot of money, so he must be. So I trusted him. At the age of, he was 20 at the time. So at the age of 20, he's already an adult, young adult, but adult. As a parent, I was convinced that I need to let them make their own mistakes. As a parent, to me, again, this is my opinion. I definitely don't regard myself as an authority for parenthood. Children learn best from their own mistakes. You just need to be there as a parent, as a safety net, so that the mistake would not cost too much. That's it. But you can't really put your child in a fluffy environment so they won't be hurt. Failing is a very good experience. People who are successful all the time, whenever a problem arises when you can't help it, sometimes they break down. So you need to have some failure. So if you want to go to your parents and say, look, this is what I want to do, from your point of view, the best answer is go and do it, and I'll sort of be there if you fail or if you don't manage. So it's not a great answer, I'm sure, but the idea is, you need to be as supportive as possible, yet letting the child do their own thing. I hope this helps. The other thing is just to remember that what John Lennon said, he just actually quoted someone else before. Life happens when you make other plans. Okay, so So you can make plans, but then things happen randomly, and you need to navigate your life through that. And sometimes you look back and say, actually, this chaotic life, this randomness, led me to a very good place, without me actually engineering this place. That's it.
Thank you, sir. I hope the students have enjoyed the lecture, and sir has beautifully explained. He was talking about the granular materials and the self-organization in them, which he's working on. And apart from that, sir has also given you some of you must have benefited with. And students, if you have any other questions, then also you can talk to sir if you want to, as the student asked about just now. So if you have any other question about some information you want to have, some life lesson you want to ask, you can go ahead with it. And we are guests will arrive soon, and now first Dr. Gurinder Singh Garewal, and I also invite sir for vote of thanks.
Thank you very much, Professor Raffle. You made it by the short-term request. I must share with the students, I have proposed them if we can have a long-term relationship with the University of Cambridge. He is going to work on it, he will try to work on it. If something works out, it will do a lot of good to these youngsters for the coming days. We hope and pray that he will do something about it, and we will also cooperate in that, so that we have some sort of a student exchange program with the University of Cambridge. So I have no words to express my gratitude to you, Professor. I hope you will keep on sending your colleagues also here. Sometimes whoever is coming, we will be welcome to have you. Thank you very much. I am actually thankful to his wife, Frances. She is the one who organized this talk. I requested her if you can take him a talk, and she agreed on that. And Francis, we want a commitment that anybody coming from Cambridge and this part of the world will come and give a talk here. Yes. Francis is a very well-known clinical psychologist in the University of Cambridge also. So I want to thank both of them. And with us done, after this, I think now we will go for a quick lunch and then move further. You want to say something?
To say something, oh, thank you. So I'm not prepared for this, but just wanted to thank you for your hospitality. It's been very heartwarming to see the lovely school you have, and to meet your teachers, who obviously are very dedicated to your education, and I wish you all well in the future. Yeah? You should fulfill your dreams.
Thank you, ma'am.
all a very warm welcome to Madam Francis and an equally warm welcome to Sardar Sandeep Singh Garewal, who has joined us in today's lecture. And it is worth mentioning that Mr. Garewal is IAS of first Indian batch and former Cabinet Secretary, Government of India. His son of late Mrs. Sarla Garewal, IAS and former Principal Secretary to Prime Minister, former Governor of Madhya Pradesh and President of Tribune Trust. We welcome you, sir. Thank you so much for sparing your time. Now we will like to honor Dr. Rafael, Madam Francis and Sardar Sandeep Singh Garewal. I request Manager of our Trust, Sardar Gurinder Singh Garewal, Principals of our institutions, Dr. Amandeep, Dr. Stinder Kaur, Mrs. Daljit, Madam Sandeep, and Dr. Pawan. I request all the principals to join very well, sir, in honoring. Thank you, sir, for sparing your precious time. We would also like to give token of love to Madam Francis. Thank you, ma'am. Ma'am's training is also equally interest in clinical psychology. I really miss, we could have had a conversation with Madam Francis also on topics of psychology. And we are honoring Sardar Sandeep Singh Garewal. Thank you, sir, for sparing your time to be part of this function. Huge round of applause. Those are the ones displayed over there, ma'am. They are the traditional artifacts of Punjab. So we would like you to have a look at them.
Earlier, these were the shipment is called shipment. So people used to carry chapatis in it. The old traditional. This is in the small size. That is like that. The older one is good. I'm going to show you. The original one. This is the original one, ma'am. This is the original one. It is the impact to carry the chapati. Chapati like a casserole. This is called kiddo. People used to play with it.
What is this used for?
Kiddo is played with ball.
Sir, right now we use the handball. No, sir. We
Not
used
for
to play.
cricket.
No, not for handball. We
Not
use
for
na handball. We play these days. And the earlier one in India, we used to play with this. That is the same one. That now it has been established as a handball.
What's inside?
Inside the waste of clothes or whatsoever is the wastage of that, they convert it to. Yeah. So it hit very hard.
This is
Okay.
Acupressure.
Okay.
right now, if you want more stressful.
If you want to take, if you want to take anyone,
Yeah.
if you want to take anyone from
Any
this,
of
you can put into your drawing room as in.
After that, you can ask me the grade.
I can ask.
Right question with right person.
And this is the seater. We handmade seater. People use
This is my kid. Where is this one?
students like are fashion designing or are board students. People used to sit here.
which one, what's your favorite?
What, to choose for me? Yeah. Oh. Can I take this one?
Then it takes a long time.
Yeah, no, I can see. It's very easy to get around.
This is also made by our students. Purple car. This is Korean car. Made by our students.
How long does it take to make something like that?
Maybe 6 months, or if they full time, then 2 to 3 months.
You can choose any item.
This is sir.
They're all beautiful.
Coasters.
No, no, you can choose any
That's a
item.
coaster.
You can put on your table and hold your glass on it.
Yeah, Francis tells me that I never use coasters, but she said they're huge.
So I'm going to give you some things and you can use an additional Punjabi things in it.
Okay, thank
You
you.
did that.
Thank you very much. Yeah.
Yeah. So these all things are, this is the Betsy sweat. We will do a Betsy sweat. It also take at least 2 months.
So these are students in the art
Art classes made this. Ma'am, these are made by, all things are made by
Yeah, this is very useful.
and this is
Ma'am chose,
Khalsa College.
ma'am chose by herself.
And this is a coaster. You can use the coaster for sun.
Okay.
This I do.
because
Very, very important.
This is that if you want to bring, and we can give you.
Would you like to carry that?
Carry some to your UK.
I don't think we can take this into the UK.
You can put into your suitcase and luggage and.
This is very,
I'm going to come to UK by February, then I will bring this one for you.
okay.
My
When will you
daughter
come?
is, my daughter is there in Bristol.
In Bristol.
Bristol.
Okay,
Then I can bring this one.
that's a deal.
That's the thing.
This is beautiful then.
Yeah. Yes, sir.
I have one here.
We have many. This one, this is Koshia, this one is Koshia,
What did you choose?
yeah. This one is very beautiful.
Okay, yeah, that's a very beautiful rose.
Yeah.
Thank you, yeah, these are very lovely.
This is like Alparanga. And this is also made by the students. With the thread, with the thread. With the thread. This is called I will Indian breads, all chapatis, Indian doctors. Here, the old ladies used to put tortillas in it. This box, it's the tortilla.
Ah, I see, okay, yeah.
Here, this one is the, this one is the, this one is the.
size to take my bag.
Due to time constraint.
Yeah, it was also, yeah.